In some parts of Britain, we have a tendency to take water for granted. But supplies are not always readily available, and this poses special problems for the fire service at some incidents, such as on motorways or in rural areas. In an attempt to make efficient use of limited water supplies, many fire brigades have adopted hose-reel systems in conjunction with additives, such as foams or wetting agents. It is widely believed that additives can help bring fires under control more quickly and reduce the amount of water required. But how successful are they in practice? To find out, the Fire Experimental Unit at Moreton-in-Marsh carried out a 5-year program to assess the relative qualities of the different products available when used through hose-reel systems and the impact of their usage on firefighters and their equipment. Major points covered in the study were trials to establish which additives improved the control and extinction of various types of fires, investigations into the tactical variations possible when using additives through hose-reel systems, for example, the use of jet or spray, and primary or secondary aspirated or unaspirated applications. Primary aspiration is where foam solutions are passed through a foam branch to produce foam for application. Secondary aspiration is where foam solutions are applied other than by a foam branch. By this method, however, the foam solutions will still take in air and produce foam of a sort. Some additives used during this work are not intended to be applied as foams. These are referred to as being applied unaspirated. Studies were also made into the chemical effects of additives on firefighters, fire appliances, and firefighting equipment. The results were sometimes surprising. For example, in certain situations, the use of water alone proved more effective than some additives when extinguishing fires. In order to cover a wide range of possibilities, a total of 11 additives were tested in separate trials, involving fires with a Class A fuel, wood, a Class B fuel, petrol, and various non-standard fuels, tires, polyurethane foam, and alcohol. Most of the fires were fought with an Angus Superfog hose-reel branch, chosen because it's widely used by brigades. Where primary aspiration was required, an aspirator was clipped onto this branch. This was removed for those additives which were applied secondary aspirated or unaspirated. The additives tested were aqueous film-forming foam, alcohol-resistant AFFF, protein foam, fluoroprotein foam, alcohol-resistant fluoroprotein, film-forming fluoroprotein, alcohol-resistant AFFP, synthetic foam, fire-out, a wetting agent, and halo foam, a self-foaming additive. The trials with the Class A fuel, wood, revealed large variations in the relative effectiveness of different additives. These tests involved extinguishing fires in British Standard dry wood cribs. The trials ranged in size from a small fire in a single crib to a large fire in a test room containing half a ton of wood in several cribs. The small fires were carried out in order to select additives for evaluation during the large fires. They were fought by an experienced firefighter using small primary aspirating and secondary aspirating nozzles, delivering solutions at 9 litres per minute, equivalent to the flow delivered by a portable fire extinguisher. None of the additives tested here performed significantly worse than water, and so all were selected for use during the large fires. The large-scale crib tests were carried out in a purpose-built test room constructed of brick with a flat reinforced concrete roof. The fires were allowed to burn for 8 minutes before firefighting commenced. 2 methods of attack were employed. For the secondary aspirated and unaspirated trials, the branch was mounted on a rotatable rig. This enabled the firefighting to be repeated in an identical manner, providing an accurate basis for comparing the relative performance of the additives tested. The branch was operated at a flow rate of 100 litres per minute and was set to give a spray cone angle of 26 degrees, so that the spray just wet the front surfaces of the cribs over their entire height. In order to compare the relative performances of primary aspirated and secondary aspirated applications in a realistic situation, some fires were hand-fought from the doorway. The firefighter used either primary aspirated AFFF, secondary aspirated AFFF, or water with no additives. All the additives tested, with the exception of fire out, were more effective than water alone in reducing the severity of the blaze, but none extinguished it completely. In general, AFFF and halo foam produced the best results, with FFP, alcohol-resistant AFFF, and synthetic foam also performing well. When the different costs of these additives were taken into account, synthetic foam gave the best cost performance. Disappointingly, none of the products tested showed much improvement over the use of water alone in reducing air temperature within the test room. This air cooling is important because it governs the amount of time before a firefighter can enter a room to make a close-range attack. AFFF was marginally more effective at this, while halofoam and alcohol-resistant AFFF actually performed worse than water alone. Nor was there any significant improvement over water or secondary aspirated foam in reducing the severity of the fire or in cooling the air when a primary aspirated nozzle was used. The FEU concluded that the use of additives in house fires was unlikely to reduce fire damage or achieve savings in water to any significant extent. They could, however, prove advantageous where the vital consideration was to bring the fire under control in the shortest possible time. The trials with Class B fuel, petrol, produced more clear-cut results. Small-scale tests were conducted to develop trials techniques and to give indications of additive performance. Of the additives used here, only fire out was eliminated from further testing during the large-scale fire tests. These tests were carried out in a purpose-built concrete tray measuring 40 square meters and containing 1,000 liters of 4-star petrol on a water base. The fuel was ignited and allowed to burn for 1 minute. Then, tackled by an experienced fire officer with a hose-reel branch operating at 100 liters per minute. After the fire was extinguished, a burn-back test was carried out on the foam blanket to assess its resistance to flame. All of the additives tested performed badly when used secondary aspirated. Some tests showed that the fire could easily redevelop after extinction, putting firefighters at risk. In each case, the fire took more than twice as long to extinguish with secondary aspirated application than with primary aspirated application. This table shows the average extinction times achieved by the 3 additives, which performed best when primary aspirated: AFFF, alcohol-resistant AFFF, and FFP. Fluoroprotein foam gave poor performance when used primary aspirated through the hose-reel branch with an aspirator. However, when applied through a better non-hose-reel foam-making branch, the results were acceptable. Use of a primary aspirator also resulted in superior burn-back times. FFP performed best here, preventing full burn-back for more than 10 minutes. The tire fire tests were designed to simulate incidents involving vehicles rather than tire dumps. Tire fires often occur when underinflated tires or binding brakes result in spontaneous ignition through friction. HGV vehicles on motorways are particularly prone to these problems. Many brigades consider tire fires difficult to extinguish with water only, but these tests indicated that this is not necessarily the case. For the main trials, 2 deflated HGV tires were heated to 160 degrees Celsius and mounted on a rig which was lowered into a fire tray containing petrol floating on a water base. After the petrol was ignited, the tires were left to burn for 5 minutes before firefighting began. An experienced fire officer, using an Angus Superfog hose-reel branch, hand-fought all of the fires. Two basic tactics were used: a close-quarters attack using the branch on a half-spray setting, and a longer-range attack using the branch on a very narrow setting. A flow rate of 100 litres per minute was always used. These different tactics had a profound effect on the impact of the additives. When the firefighter was allowed to tackle the blazing tire at close quarters, water achieved a quick extinction in 16 seconds without the need for additives. But when the firefighter was told to attack the flames from a distance, the additives improved the extinction times significantly. Water alone took an average of 2.5 minutes to extinguish the fire, whereas all of the additives tested, with the exception of the wetting agent, performed better. The fastest extinction time was achieved by synthetic foam, 3/4 of a minute when applied primary aspirated. Fire trials were also performed on polyurethane foam cushions mounted on a rig resembling a two-seater settee. From the results of these fire trials, it was concluded that the fires of polyurethane foam commonly encountered by brigades and fought with hose-reel systems, such as in house fires, were easily extinguished with water alone. Tactics proved an important factor in the alcohol fire trials involving the polar solvent fuel isopropanol. This liquid is widely used in industry and presents a severe test for alcohol-resistant additives. Circular trays of burning fuel were fought with a small foam branch pipe. Tactics ranged from forceful application, where the jet was plunged directly into the isopropanol, to gentle application, where the foam was allowed to strike plates around the tray and to flow onto the fuel. These different methods of attack produced dramatically different results. Forcefully deployed, alcohol-resistant AFFF took nearly 16 minutes to extinguish the fire. Applied gently via a front plate, it took just over half a minute. Water alone still failed to extinguish the flames after nearly 3/4 of an hour, and alcohol-resistant additives proved the only effective means of tackling these fires. Conventional additives also fared badly, proving slow to achieve extinction and offering no resistance to burnback. High foam application rates are necessary when fighting alcohol fires, so it was concluded that hose-reel equipment and alcohol-resistant foams could only sensibly be used on small alcohol spill fires. Here, the best tactic would be to bounce the jet off an object or a surface near the burning fuel, so that the foam flowed gently over it, forming a blanket to smother the flames. If the object aimed at was cooled before application, results were likely to be even better. As well as looking at the effectiveness of additives in fighting a fire, it was decided to investigate the chemical effects that these agents could have on firefighters and their equipment. The work studying the chemical effects on equipment was split into three main areas: a preliminary investigation, a brigade questionnaire, and corrosion testing. The FEU commissioned independent consultants to undertake the preliminary investigation. They advised on the probable corrosive effects of additives and water on fire appliances and associated equipment. They also recommended a suitable method for testing a foam's corrosive properties. A questionnaire was sent to 67 brigades. Of those, 35 reported corrosion problems caused by water, against 25 listing corrosion caused by additives. Protein and fluoroprotein foam additives were reported to have caused severe corrosion to steel and aluminium alloys in bulk storage containers, pipework, and valves. Synthetic foam was said to have broken down the epoxy lining of one appliance's foam tank. AFFF reportedly caused blockages in induction systems. As a result of the recommendations made in the consultant's report and the information in the questionnaire, 2 series of corrosion and degradation tests were undertaken by the consultant. The corrosion testing showed that mild steel was not suitable for storing undiluted additives or even water. Of all the materials tested, only UPVC and stainless steel showed excellent resistance to the chemical effects of all additives as well as water. As far as health hazards were concerned, it was concluded that these were minor when additives were used normally. But if prolonged contact or splashing was likely, then it was advised that firefighters should wear protective clothing, such as gloves and goggles. The unit's comprehensive work over a 5-year period on the use of additives through fire appliance hose-reel systems is detailed in a series of 6 reports. Viewed as a whole, they confirm the fact that while chemical additives are highly effective in certain types of fire, this is not necessarily a general rule. Where access to the fire was limited, improvements in hose-reel firefighting efficiency and consequential water savings were small when used to tackle Class A fires. But there were significant improvements with certain additives against tire fires. Little or no improvements were found when fighting Class A, tire or polyurethane foam fires where access was not restricted. Water is not recommended for fighting Class B or alcohol fires. However, the use of hose-reel systems with certain additives and primary aspirating equipment resulted in convincing control and extinction of Class B fires. Similar performance can be expected when fighting alcohol fires, except that the high application rate required will greatly limit the size of fire that can be fought. In deciding on the merits of applying additives through hose reels, brigades should base their decision primarily on the relative importance they attach to tackling small Class B fires and tire fires.